is page like 7 in the notes, counting like the front and back part. But at the top it says alkene carbocation forming mechanism practice. This deals with just the Markovnikov reactions that were covered in the video. So this is immediately following the notes. It's got 1 through 4 on the front and then 5 through 9 on the back. We're going to go through 2 of them together, and then you'll be able to go through and practice with people around you and then check answers as well. So I'll have the answers up here for you to check. So we're going to start with looking at number 4. 1, 2, and 3, and you'll notice, like on the side in red pen when you look at the answer key, 1, 2, and 3 is hydrohalogenation, which is adding HX like we've been doing. When we were looking at forming carbocations last week, we were looking at adding HBr, HCl. 1, 2, and 3 is looking at that. So those are the ones that we've looked at before. Number 4 is where we start, right, to see HNO3, H2O, different reactants and different solvents on the arrow. So remember the arrow tells us reactants and solvents. So on the top here, all right, this is either a catalyst or a reactant, and then the bottom we have a solvent. So if we look at what's over the arrow, we have an acid and we have water. So if you look at your notes, right, the notes talked about hydrohalogenation, which is adding a hydrogen halide. It talked about acid-catalyzed addition of water. And then on the back, the last thing it talked about was the acid-catalyzed addition of an alcohol. And so when we look at this, all right, we have an acid and we have water. So this is looking at the acid-catalyzed addition of water. Now, this says draw the mechanism and the major product of the reaction. Remember, as we go through for organic, we always have to show any formal charges that occur throughout the mechanism. And I'm going to kind of go down and around in the circle. So we're going to show the mechanism kind of down and around, and then the final product will be up here. And I'm going to try to use different colors as well. If it helps you to use different colors as you go through, by all means, use different colors. You'll even notice on my answer key, like I did it in pencil, but I was showing the curved arrows in blue pen, and then I was labeling like carbocations in purple. I just like seeing things in different colors. If you're like, no, I'm good with pencil, okay, all right, use pencil. So we're starting with an alkene. All of these reactions that we're looking at are starting with alkenes. Remember, an alkene has an excess of electrons. This pi bond, those are our excess of electrons. Now, when we have an acid and water, right, acid-catalyzed addition of water, the mechanism actually starts with the alkene attacking the acid. So it starts with the alkene attacking the acid. And now the way that you'll see the acid written is actually with the H bonded to an O and then just the rest of the acid. We are worried about the acidic hydrogen. And then we're showing it bonded to one of the O's because that's actually how it's bonded. And then we just do NO2. We don't really care about the rest of the Lewis structure. But this is going to allow us to show that curved arrow movement. So the first thing that's going to happen is the excess electrons. Right? The only place there's excess electrons are the pi bonds here. These excess electrons are going to attack that hydrogen. So now this hydrogen has 4 electrons around it. Should only have 2. So the electrons in this bond are going to move directly to the oxygen. There will be side products, and it looks like we're just ignoring them because we kind of are. All right, we're not worried about the side products that are forming here. So this is actually, if we think about, right, acid-base reactions from last year, we now are getting this H. Now we're going to form NO3 minus. All right, we're forming actually a neutral conjugate base. We're not worried about the side products. We're only focused on these major products. Anything that's formed on the side, we're just ignoring. I'm not even going to add it anywhere. So after it attacks this hydrogen, Right, again, I'm going to kind of work down and around, and I tried to give you some space to do the same thing. Remember, these are Markovnikov reactions. What that means is the carbocation is going to form on the more substituted side. So we've now lost the double bond. Here, there were 2 hydrogens already, right? Hydrogen, hydrogen. Now there are 3. The third one came from this hydrogen. I'm not showing them, but sometimes you'll see it like this. Just remember that there are still 2 other hydrogens here. This is just showing the hydrogen that came from the acid. And now we have a positive on this carbon. All right, so now we formed a carbocation. Now, something you always just want to do a quick check of is, okay, is there any way that I could make this more stable? Because right now, this is a secondary carbocation. Well, if I move the positive charge over here, that'd only be a primary. That's less stable. We move it here, that's also secondary. All right, so if you move it and it's still secondary, it's not worth the energy to move that carbocation. So this is the carbocation that we're going to use. So now we've used the acid. All right, that was the catalyst. It started this process. Now we focus on the solvent. All right, water here is the solvent. Remember, you have lots and lots of the solvent. It's everything else that's in the container. And so now we're going to have plus. I'm just going to do H2O like this. If you want to actually show the whole Lewis structure, that's fine. I'm just going to show it with the 2 lone pairs because we're really just focused on the 2 lone pairs on that oxygen. So now we have a positive here. Oxygen has an excess of electrons. So 2 of the electrons are going to come from the oxygen to that carbon. When you move lone pairs to that carbon, that's creating a bond. So now we've created a bond between this carbon and this oxygen. Now that oxygen still has a lone pair and it's still attached to 2 hydrogens. So what this will actually look like, I'm also going to ignore this hydrogen now. Right? This hydrogen didn't disappear. I'm just going to ignore it. I'm just going to say, okay, it's CH3 on that side. So now here we have O bonded to 2 H's and a lone pair. So O is bonded to 2 H's and has a lone pair. Always pay attention to formal charge. Oxygen typically wants 2 lone pairs and 2 bonds. When it has 3 bonds, it's now going to carry a formal charge. Because oxygen has 6 valence electrons. If we think about formal charge here, there's 1, 2, 3, 4, only 5 electrons around it. So this is now going to carry a positive formal charge. Now if you say, well, how do I know that that's not my final product and that another step is going to have to occur? Final products typically are not going to carry a formal charge because there was no formal charge to begin with. So we shouldn't see formal charge in the final product either. And so what we're going to do is we're going to look at using more of the solvent. We're going to use more of the solvent because we have lots of H2O. You essentially have unlimited solvent. We're never going to have to worry about using up all of our solvent. So when you draw this, right, just think, okay, here's another lone pair, negative electrons. This oxygen is positive. So when you think about how can we change that formal charge, we don't want to give it another bond. Right? But what we can do is this oxygen can attack one of the hydrogens. When it attacks one of the hydrogens, the electrons from this bond are going to move to the oxygen. Because now oxygen will have 2 lone pairs and 2 bonds, which is what oxygen wants, to give it a 0 formal charge. And so that's going to create H3O+. Again, another side product. We're not worried about any side products. but we would see that H3O plus forming. We're worried about the organic product. So we redraw this. Now off of this carbon, these electrons went back to the oxygen, and now there's just one hydrogen. If you want to show the lone pairs, you can, but you don't have to. That oxygen now has a 0 formal charge, 2 bonds, 2 lone pairs. Now, if this just said draw the major product, this is where this reference sheet actually just shows our products for these different addition reactions. So when we have water and H+, that just means you're adding an acid. You can see where that alcohol is added to. All right, the alcohol is added to the more substituted side of the double bond. It's a Markovnikov reaction. Just like a chlorine or a bromine would be added to the more substituted side. But the mechanism is showing how that's working. All right, how we're using the acid to start the reaction, and then we're using the water as the solvent, right, to move the electrons around and actually get to this final product. Questions on this one before we look at one more together? All right, so the next one that we're going to look at, and these are in the Do Now slides as well, so just these two, but we're going through them together as well. We're going to look at number 6. All right, so number 6, now take a look at what's over the arrow. What we're really going to have to start looking at, especially as we get into more types of reactions, is what is our catalyst or additional reactant and solvent? Because that's going to determine what type of reaction we're looking at, especially when we get into anti-Markovnikov reactions, right, where it's just the opposite of what we've been looking at. It's all about what is being added to that alkene. So we notice, again, we have an acid. So HNO3, again, I'm just going to write like this, HONO2. We're only concerned with that acidic hydrogen. But then down here, this is not water. I see this, right, HO. We're used to seeing it as OH, but when you have HO, it's the same thing. It's an alcohol. So now we have an acid, and we have an alcohol. So now this is the acid-catalyzed addition of an alcohol instead of water. Similar, right, similar to water, but our final product is just going to look a little bit different. So again, we start by using this catalyst to kind of jumpstart the reaction. The alkene, excess electrons come from the pi bond. Then, because hydrogen can only have one bond, right, these electrons that are in the bond between hydrogen and oxygen are going to go directly to the oxygen, gives us NO3 minus. All right, again, NO3 minus here is a side product. We are not concerned about side products. We are concerned about the organic material that's going through the mechanism. So after these excess electrons attack the hydrogen, because this is a Markovnikov reaction, the hydrogen is going to add to this side. Now remember, there were already 2 hydrogens here, so you're just adding that third hydrogen to make it a methyl group. So that means that the positive carbocation, right, the positive formal charge, is going to be on this more substituted side. When you form a carbocation, always double check and see, is there a way that we could make it more stable? Right now, this is a secondary carbocation. Has 2 additional things, not hydrogen, attached to it. Now remember, right here, here's a methyl group, but this carbon doesn't have a formal charge, so it has 4 bonds. It has a hydrogen attached to it as well. We just don't show hydrogens in these bond line structures. Now, at first, when I looked at this, I was like, okay, well, if I move my methyl over here, that's still going to give me a secondary carbocation. But if we move the hydrogen, move this hydrogen over, if we move this hydrogen over, what's going to happen is we're going to take this structure, the methyl is still here, I've just moved the hydrogen over here, so now this carbon only has 3 bonds. I've now moved that carbocation from secondary now to tertiary. So you always want to do a quick check to see, can we make our carbocation more stable? So this is a hydride shift. You can either shift a hydrogen or a methyl group over only 1 carbon, no more than 1 carbon. Now that we have the most stable carbocation here, now we can continue with the mechanism. Now, I'm going to draw this so you can see what this looks like. All right, so here is the HO. This oxygen is bonded to a C, so here's a C. And then there's 3 methyl groups off of this carbon. So it's like this alcohol has like 3 fingers sticking out. I'm drawing this because that's how I'm going to show this over here. So there's a carbon here that connects those 3 methyls. Now again, when you have a positive formal charge, that means that it's going to be looking for some negative. Lone pairs are negative. So we have these lone pairs from the alcohol that can go, right, and that's going to this positive, so it should go all the way down. I just want to make sure you can still read the tertiary in that positive. So we have the lone pairs attacking that carbocation. That's going to form a bond. Now here's where it starts to look really weird. Just draw it the best you can. So, okay. All right, so off of here now, I have O, still bonded to H. Now with 1 lone pair, carbon, 1, 2, 3 methyl groups. All right, so it starts to look weird when you're adding everything to it. Just take your time as you're drawing it. The reason that I drew both of them down is because, remember, you don't want to have any groups pointing up, right, within that V. You want everything to kind of be as far apart as possible. Now, right now I'm missing something from this because oxygen has a single lone pair and 3 bonds. That gives this a positive formal charge. So we're not quite done yet, because oxygen should not carry any formal charge in the final product. Well, remember, this is the solvent. We have lots of the solvent. So now we're just going to use more of the solvent to try to get rid of that positive formal charge. The reason that these lone pairs are not attacking this is because that's giving oxygen another bond. To get rid of oxygen's positive formal charge, we need to somehow get it another lone pair. To get it another lone pair, we could pull off this hydrogen. All right, so these lone pairs are actually going to attack the hydrogen. And then the electrons from the bond are going to go directly to the oxygen. Now again, when this alcohol attacks this hydrogen, you're going to get an additional side product. We are not concerned about the side product that is forming from this alcohol picking up an extra hydrogen. What we are going to look at is what this product becomes. So, all right, so now here we have this oxygen. I can put the lone pairs on in a second. This oxygen is bonded to one carbon, which is bonded to 3 methyl groups. If you want to add those lone pairs, you can. But by removing this H, by the alcohol removing this hydrogen, it gave this oxygen that additional lone pair it needed to reduce that positive formal charge back down to being 0. Now, if you look at the difference from the original alkene to this product, normally, right, we would form, right, whatever this new substance is, we would actually form it off of the more substituted side of the alkene. But notice it actually formed off of one carbon over due to that carbocation rearrangement. So there are times it can rearrange, so you just have to kind of pay attention a little bit to that. But when you're adding an alcohol, you're forming an ether. When we added water, we formed an alcohol. The only difference between this and just adding a halide, HCl, HBr, is just this additional use of the solvent to create either the alcohol or the ether. So this looked at kind of 2 of the more advanced mechanisms with these Markovnikov reactions.
So on the final product, could you have the O on the other side? Could it be flipped around?
Like these 2?
Yeah.
Yeah.
Okay.
As long as off of this carbon you have the ether and a methyl group, whether you have it like the ether on this side and the methyl on this side, that doesn't matter.
Okay.
Yep. Yeah. Other questions on this one? All right, so if not, I'm going to give you guys some time just to work through this practice. All right, we have about 12 minutes. If you don't get this done, we'll keep working on it tomorrow. Working on these mechanisms just takes practice, right? So work through. I have the answers here, so you can go through, check answers. You want to take pictures of them, you can. 1 through 6, you're actually showing the mechanism. 1, 2, and 3 should look a little bit more familiar because those are the ones we've been doing with carbocation rearrangements. And then 4, 5, and 6 are the ones that are looking at the acid-catalyzed addition of either water or an alcohol. Okay, so you can come up, take pictures. Use this reference sheet as well, just so you can kind of see, okay, here's how the alkene started. All right, here's what the product should look like. That kind of just helps you to see, were you on the right track or not. There are a couple that rearrange. So we looked at one of them. There are 2 additional ones that rearrange in terms of the carbocation.